thanks very much for having me. So great to get to start things off. So I'm going to talk about like a really basic question, which is, let's say we're given an element, let's say in C-star algebra of, let's make it easy, let's say the free group, okay, on n generators, is x a positive operator, okay, meaning pick a representation on some Hilbert space and then say positive, say in some representation we have v star xv is greater than or equal to 0 for all of v, okay, positive. And it looks like it's going to be a really short talk because we have an answer to this question, right? The answer is if and only if x equals y star y for some y in C star Fn. Okay, so talk over, that's the answer. Of course, we want to make it like a practical problem we can implement on a computer. Well, how would we do that? We first of all have to look at this and say, what does it mean to be given an element of a C-star algebra? We can't really be given an element of an abstract C-star algebra so easily, so we have to cross that out and replace it with something. And maybe we're going to replace it with, well, maybe we don't care about all the elements of the C-star algebra, so it would be good enough to replace it with elements in the actual group algebra, linear combinations of the group elements, okay? And right away we have a problem because now this answer isn't true anymore, okay? But fortunately, we do know the answer to this. We can thanks to Piconia and Timotin. The answer says that x is a positive operator. Oh, you might ask, what does it mean to be positive now in just a regular algebra? So what we'll say is positive in all representations on Hilbert spaces. So we want in every representation, we want this x to be positive. And then Piconia and Timotin say, oh, this happens if and only if x is equal to the sum over yi star yi for some y1 to yn in our group algebra. So it's no longer true that we can always write every positive element as a square, as a Hermitian square, but they are sums of Hermitian squares. We'll see, call that sum of Hermitian squares. So more generally, maybe we're going to say, let's make sure we've got our terminology down. Maybe we've got a group algebra or some other star algebra, and we'll work with the actual algebra itself, okay? So let's see. It's a bunch of different terms we can define. So yeah, we'll say, x is positive. We covered this one. If ix is greater than or equal to 0 for all representations, phi from A to B of H. Let's see. It makes more sense to carry this around with me. We'll say x is finite dimensionally positive, FD positive for short, if we have the same thing here, okay, so phi x is greater than or equal to 0 for all representations, but now it'll go phi from A to B of CD, some D. Okay. We'll say that A has the SOS property. Sometimes this is also called Archimedean closed if we're talking about an Archimedean star algebra, but let's call it SOS here. If being positive is equivalent to being a sum of Hermitian squares, like in our free group case up here, and notice what this means. The point of this SOS property is that when something is positive, we can always prove that it's positive, okay, by giving y1 up to yn. So being SOS is about having proofs of positivity. And then we'll say A is RFD, residually finite dimensional, if finite dimensional positivity and positivity are the same thing. So if X is FD positive, if and only if X is positive. Okay. And this one, it's not really actually what we should call RFD for A as a star algebra. It really is RFD of the universal, enveloping C star algebra. Okay, but it's about being able to prove something is non-positive. Okay, so if we know that if A is finitely presented, okay, so in other words, if it is of the form the star algebra given by some generators, subject to some relations, and is RFD, then we can prove non-positivity. And why is that? Well, let's say that we have an element which is non-positive, okay? Then it has to also be not finite dimensionally positive, which means there has to be some finite dimensional representation where we see that it's not a positive operator. And how do we know if something is not a, well, first of all, how do we know that something is an actual representation of an algebra? In general, that might be hard to check. But for a finitely presented algebra, a representation is just some collection of matrices satisfying the relations. Okay, so we look through collections of matrices that satisfy the relations. If we find one, or if we're given one as a proof, where all the relations are satisfied, and we see that our operator X ends up not being positive in that representation, then we have a proof that it's not positive. Now we might wonder, is something like Baconian-Timilton always true? Can we always find a sum of squares proof of positivity? And it's very close to being true. Okay, so we have what's called the Helton-McCulloch positive Stellensatz. Which is that X is positive. This is actually for Archimedean algebras. I've left that, well, for group algebras it's fine, okay, but this works in general for Archimedean algebras. X is positive if and only if for all epsilon greater than 0, X plus epsilon is equal to a sum of squares. And the order of the commutators is important here. The sum of squares decomposition we get could depend on the epsilon that we pick here. Notice this is interesting because it doesn't actually give us a way to prove either positivity or non-positivity. Okay, so if we want to prove that something's positive with this, well, maybe we pick an epsilon, and we know that X plus epsilon is a sum of squares. It tells us that X plus epsilon is positive, but it never actually tells us for sure that X itself is positive. We have to check all epsilon. And similarly, if we are looking at proving something is non-positive, well, how do we prove something is not a sum of squares? We could check up to a certain degree maybe in our algebra, but how do we know that there just isn't a sum of squares decomposition with higher degree? We don't get a way of actually proving something's positive or even proving that it's non-positive out of this criteria. So it's kind of interesting to contrast to the other two conditions we looked at. So that's kind of the point of looking at conditions like SOS and RFD, especially if we put them together, right, is that you know, for finally presented algebras, we have SOS plus RFD, then we can decide positivity. And how do we do that? Well, what we do is let's say, are given our element, we go through sum of squares decompositions and look for one to prove it's positive. And at the same time, we go through representations and look for one where our operator is non-positive. Okay? And one of those is eventually always going to terminate if we have these two properties. And whichever one terminates, we know that's whether, that tells us whether our operator is positive or not. think it's helpful to see some examples. Okay, so the first thing to look at is just the commutative case. And the first algebra we might want to look at there is just ordinary polynomials. Okay, so the study of sums of squares is a pretty old topic, all right? And for commutative polynomials, there's a famous Hilbert's 17th problem, which asks whether every, so it was known, so for n equals to 2, positive elements are sums of squares here, okay? But for n greater than or equal to 3, they're not, okay? So for n greater than or equal to 3, this algebra is not SOS. So we can't prove positivity with sums of squares. But then Arden's solution of Hilbert's 17th problem is that you can always write every positive polynomial as the sum of rational squares. So every positive element rational just means you have well, rational functions, so denominators which are polynomials as well. And this gives us a way to prove positivity for polynomial algebras, not with sums of squares, unfortunately, but with something fairly close to that. Another example in the commutative case, if we want to actually do a group algebra, okay, so if we do just the group algebra of Zn, all right, so n commuting unitaries for our representations, there's a result, oh, so this is RFD, okay, which is what we expect from the commutative case, and there's a result of Scheiterer, says that this is SOS if and only if n is less than or equal to 2. Okay, so again, for n greater than 3, that's not SOS. Even though it's not SOS, we can still decide positivity here. And this tends to be the case for commutative algebras, that we usually can decide positivity as long as the algebra is reasonable enough, and this includes like that's reasonable enough is pretty broad in this case. So we can use Tarski quantifier elimination. That's one method. Or there is what are called effective positive Stellensatz. So you might look at 1 and 2 to Perucci, Lombardi, and Roy. Fairly recently, actually. And they give ways of basically proving positivity. So for every positive element, there is some certificate that it is positive, okay? And it's effective, which means that unlike situation up there where we were like, well, if something's not a sum of squares, how do we know? We might have to keep checking higher and higher degrees. When we say something's effective, there's some cutoff that says you can search through all certificates up to this size, and if there's not one of this size, then you know it's not positive. So we have a variety of methods usually for commutative algebras of proving or deciding whether things are positive. And then, well, what about non-commutative algebras? We've already seen one example. Okay, so let's go back to this one, the free group. So this is SOS and also RFD. We saw the SOS result there is due to Baconian and Timotin, and I think RFD is actually due to Choi, if I remember that correctly. Another example we might look at here for quantum information is, let's say, take the group Zm, the cyclic group of order m, and let's take the free product of itself with itself n times. okay? Which is the same as the algebra. If we give it in terms of generators and relations, we can say it's generated by P, I, and J. I going between 1 up to n, and J going between 1 up to m, where each one of these elements is self-adjoint and a projection. Okay, and the sum over J of P, I, and J is equal to 1. So this is the algebra of n m outcome projective measurements. Okay, we have, and if you're wondering why these are the same algebra, well, for every unitary of order m, we have spectral projections, right? There are m of them, they add up to 1, and then we just take n copies of that. Oh, and I was going to tell you whether this algebra is SOS or RFD, and it is both, just like the free group case. So you could get this from results of Helton-Klepp and McCullough, or Helton and McCullough and Putinard. So it seems like when we look at whether we can decide, if we look at our original question, whether something is, we want to know whether something's positive in an algebra, the situation looks pretty good. We look at commutative case, which has been studied for a long time, and we say, hey, there's a pretty deep theory here, some crazy things can happen, but in general we can decide whether, there's some very general methods that let us decide whether something's positive or not. So at the end of the day, we can always tell if something, maybe we can't like practically tell because the algorithm's going to run for a long time. They're not necessarily very fast running algorithms, but in principle there is a procedure to tell whether something's positive. And then when we go to the first non-commutative examples that we might look at, free algebras, we say, oh, here it's actually almost a little better than the commutative case because things are always SOS. And if we put SOS together with RFD, we can decide positivity. In fact, it should also be mentioned for these results, they also tend to be effective, so they give degree bounds, let's say, on the degree of the polynomials that appear in the sum of squares decomposition. So we can actually just use the sum of squares property itself to decide positivity. And actually, the RFD results also tend to be positive. If something's not positive, we see it in a Hilbert space of a given dimension. So the next question would be to say, well, what if we put these two together? What if we look at things which, we take our prototypical non-commutative algebras, and let's take products of them rather than taking free products, right? So, so that would give us algebras like maybe the group algebra of Fn cross Fn, right? Or we might be interested in something like Zm star n cross Zm star n, right? In quantum information, which I guess is one of the themes of this workshop, we're very interested in this algebra because now we have a whole bunch of projections on this algebra and a whole bunch of projections on this algebra that commute with these. It's like we have a bipartite measurement scenario from this algebra. I'm going to talk about this algebra just because it's a little bit simpler to write down and talk about. Okay, but actually everything I say will apply for this algebra as well. So for either algebra, what I'm about to say holds, but again, we'll concentrate on this one. So the first thing we notice is that there's a result of Kirchberg, which says that this algebra is RFD if and only if Kahn embedding problem is true. A very famous result. And then, of course, we have
William.
Yeah.
If you get too low on that board.
Oh, the podium is in the way.
Indeed, yeah.
Okay. Well, I can't get taller, so maybe I will. I guess I can go a little.
That's okay.
Yeah. To here. This. Where's the cutoff? About like here at this height?
It depends on how high you put it.
Yeah. But if I keep the board at this height, where's the cutoff? Is it like the whole board, or right at this line? Yeah. Okay. I'll stop. I'll write this line, and then we'll go. over to there. Okay, mix star equals RE, of course, tells us that this is a fairly recent result of G. Tarajan Vivek, right, and UN is that Hahn embedding is false. Okay, so that tells us that these algebras are not RFD, unfortunately. So our hope maybe of trying to prove that we can decide positivity by combining SOS plus RFD is never going to work for these algebras. They're not RFD. Even if we know, we don't know, even if we don't know, even if we know, there we go, even if we know that they're not RFD, we could still ask if they have the SOS property. So is a SOS. And here's our theorem. So this is joint work with Arthur Mehta and Yuming Zhou. For n greater than or equal to 2, it is undecidable to determine if a given element, okay, I said CFN before, but if we really want to pass it into a computer, we're still going to have a problem with complex numbers. So let me make it even more specific, rational coefficients for a group algebra. So it's undecidable to determine if a given element in this algebra is positive. In other words, so what do I mean specifically by this? Okay, so we have a computable function which goes from Turing machines, okay, which if you don't know Turing machines, you could think Python programs or something, okay, so instructions that could be run on a computer, to our algebra. Okay, so in other words, it's going to take a machine M and go to some element alpha M, and then the property we have here is that alpha M is greater than or equal to 0 if and only if M does not halt. And what we get out of this well, first of all, we see that, unfortunately, the situation is not so nice if we want to decide positivity. So as soon as we combine products with our prototypical non-commutative algebras, we can't decide positivity anymore. And also, we can see that it also implies the algebra is not SOS. So it's not SOS. Why is that? So we get that out of looking at the kind of direction that this is undecidable. Okay, so imagine that it was SOS. That wouldn't mean by itself that we could decide positivity. But what it would mean is that if we look up here, imagine when you have a Turing machine and you want to know whether it halts, one thing you can do is you can just run the Turing machine and see if it halts. If it does, you know that it halts. Okay? On the other hand, let's say that every element of positive element had a sum of squares decomposition. You could compute alpha m, because this is a computable function, and you could look for a sum of squares decomposition for it. And if you found one, you'd know this element's positive, which would tell you that it does not halt. Okay? So you basically do both of these in parallel, and one of them will always finish if this has the SOS property, and therefore you'll be able to tell if the Turing machine halts, which is that's an undecidable problem. You can't have a problem which will decide if a Turing machine halts. till we get that's not possible. And the only problem with our argument was that we had assumed that this is SOS. Okay, so this cannot be SOS. If it was, we could solve the halting problem. Now, I want to point out that trying to prove properties of the algebra this way, like via computability, it actually is inspired by the same way that this conclusion works here, proving that the Kahn embedding problem is false. So let me say a little more about how that works. So, if we look at what MIP star equals RE says, okay, there we have a computable function, and it goes from Turing machines again to technical aspects are a little different. So there we actually have to go to the algebraic closure of the rationals, but otherwise we can go to the same algebra. Okay, and it's going to go to I guess I want to go from Turing machines to that algebra, and it's going to go M again to alpha M. And then what property do I want? I want to have that, so if M, so there's two cases. One is M halts, and one is M does not halt. Okay, and I want to write down a separate conclusion for each of them. I want to say if it does not halt, then alpha is greater than or equal to 1 in finite dimensional representations. I don't know, is that large enough to see there? So we mean that alpha minus 1 is positive, is FD positive. Okay. And the other one is that when it halts, that alpha M is, so if I do FD, it's not that. Okay, it's not FD positive. Maybe I should just write that out. Not FD positive. Okay. Yeah. So this has a corollary. That this algebra with the product is not RFD, as I said there. So why is that? So if this is finite dimensionally greater than or equal to 1, so if it was RFD, so assuming RFD, this could be upgraded here to say that alpha M is greater than or equal to 1. Okay? And that would tell us that that alpha M, this is by this Helton-McCullough positive Selensatz that I wrote up there, that alpha M is equal to a sum of squares. Okay, so once again, we would have a way of certifying that we're in the does not halt case. Now notice this is what we call a gap result. So it's not like M halts if and only if some condition. I had to write out both cases. And the two cases that are about separating, this one is saying, oh, it's not positive. And this is saying it's positive actually like greater than or equal to 1. There's a gap between the not positive result and the positive result. We can actually say it's if you think about why we might want that practically, maybe we want to say, hey, if something has eigenvalues that are like it's positive, but maybe there's an eigenvalue that's like really close to 0. Maybe we don't know with our numerical error. Maybe it should have been slightly negative, but we couldn't tell on the computer. right? A gap result is really nice. It separates everything for you very cleanly. You know, all the eigenvalues have to be greater than or equal to 1 here, right? And here we have one that's actually negative. Nice separation. And we actually need that to make this argument work. We can't do it without it because the Helton-McCulloch, sorry, positive Selensatz, only tells us that x plus epsilon is a sum of squares there, right? So how do we get that out of here? We actually say if alpha m is greater than or equal to 1, then this is equal to alpha m minus 1, that's positive, plus 1. We take epsilon to be 1, right? So if we know that alpha m is greater than or equal to 1, we get to apply the Helton-McCulloch positive Selensatz with epsilon equal to 1 to get that this is a sum of squares. We need the gap to do to make this argument work. But otherwise, kind of the same idea. Our result doesn't have a gap. It makes it a lot easier. I should say this is a very difficult theorem. This is, you know, it's a medium theorem maybe. What does that mean? It doesn't have a gap. Well, when we say m does not halt, that's if and only if greater than or equal to 0. So if it does halt, it has to have like a negative eigenvalue in some representation. But that eigenvalue could be really small. It could be like in the halting time of the Turing machine. Maybe if it runs for 1,000,000 steps, then we have something that's like, you know, minus 1 over 2 to the n, 2 to the million, something like that. That's allowed in this result. On the other hand, it's interesting to note that, let's see, do I have, well, maybe I'll skip that. It is interesting to note. I can tell if you want to hear about, we can only, time is limited, but if we want to prove that something's not SOS, we have to prove undecidability this way, okay? And like as in it has to come out with the element being positive if and only if m does not halt. And it turns out we can't do a gap result in the same way. It's not possible to upgrade this to a gap result and still use it to prove that this is not SOS. I wanted to give a few more minutes, right? So I wanted to use the last 10 minutes to show some indication of the proof of this. So how that works, we can also say something about tracial positivity. Which is for n large enough, it is undecidable to determine if an element in QFN is tracially positive. Okay, what does tracially positive mean? That means that you're positive on all tracial states are positive on this element x. Okay, so there's kind of a correspondence between tracially positive on this algebra and positivity for this algebra, right? So it shouldn't be a surprise we go to this algebra here. And I think I mentioned so our results there also apply for algebras like Zm star n cross Zm star n, and here same thing. We could put in here Zm star n, and in fact, to show you kind of how this proof works, I want to put in here Z2 star n, okay, rather than Fn. Okay. Here's the proof sketch. We're given Turing machine M, okay, and the statement of this proof, of this theorem is exactly the same as this one up here. We want to show there's a computable map from Turing machines to elements of our algebra. Now it's this algebra rather than the product algebra. Okay, so such that the element is tracially positive if and only if M does not halt. Sorry. So what we're going to do is we're going to look at the algebra, let's call it A0. Okay, and it's going to be it's going to have an uncountable number of generators and relations. Okay, so we're going to have generators x1, x2, and so on. And then we're going to have also some generators p1, p2, and so on. And then for our relations, we want the xi to be unitary involutions. And we want the pi to be projections. And then we want the following relation, self-adjoint projections here. Okay? And then we want the relation that Pn plus 1 is equal to Pn plus Xn, Pn Xn. But only if M hasn't halted after n steps. Okay? So if M halts, then at some point we're going to stop including these relations. If M runs forever, then we include all these relations for all n. That's the idea. So, so notice right away two properties, right? If M halts, so if, actually let's say if M does not halt, P0 is tracially positive. Okay, that's kind of the point, what we should get out of this. And why is that? We have oh, it is true, but actually that's not what we want. Maybe I better say it like this. Tracially 0, if that makes sense. Okay, so tau p0 equals 0 for all tracial states. And why is that? Well, we see from this that we have tau Pn plus 1 is equal to 2 tau Pn. Ah, there we go. Okay? We're looking at this, trying to make some sense out of this. At least I am. Okay? But what we have, tau Pn plus 1 equals 2 tau Pn. So in other words, tau Pn has to be a half tau Pn plus 1. These are self-adjoint projections. Tau can't be more than 1. So if this relation is running forever, okay, then tau of P0 has to be 0. Okay? That's the only possibility. And conversely, I'm not going to write it down, but this is, maybe I will write it down. I have to put an if and only if in there. It's a very simple algebra, so it's not hard to see. Okay, we can actually, I mean, it's really only got this one relation, so we can kind of write down whatever tracial state we want on this thing, as long as this relation is satisfied. And if it does halt after some point, we can find a tracial state which is strictly greater than 0, rather than just 0. Okay, and it would have to be 1 over 2 to the n, where n is the stopping point. Or maybe it's 1 over 2 to the n plus 1. So then what do we do with this, this algebra? Claim there is an embedding A0 of M into a finally presented algebra. Let's say we need some new generators because we're already using x's, so let's maybe use, oh, in fact, actually, we are going to want it to be a quotient of z2 star n, okay? So let's say we have some generators for this, and then we're going to have a finite number of additional relations. And what property does this embedding have? Such that every tracial state now 0 on A0 extends to a tracial state on A1, and to Pn plus 1, our key relation here, xn Pn xn, can be shown with Fn applications of our relations R1 up to Rn. Right? Where this is actually a polynomial function of n. And then there are some additional conditions we want in this embedding, but they're technical. I'll leave them off. These are the two I want to talk about. And then what we're going to do is we're going to set alpha m equal to sum over Ri star Ri minus P0 adjusted by some constant. Okay, so one direction, if m halts have now 0 on A0 with now 0 P0 greater than 0, right? That's what we said. It could be very small in terms of the running time of m, but we have it. So we use property 1, extend it to a tracial state tau on A1, okay? So this implies tau on A1. Tau is a state on A1, which has these relations. So tau of this part, right, is 0. Tau is going to vanish on all the Ri's when we pull it back to the free algebra. But it's positive on this part, and we subtracted that part. So what we get is that tau of alpha m is less than 0. Okay? That's the easy direction. And it seems like, so I'm not going to do the other direction, given I think I'm supposed to stop now. Okay? But what I want to say is that so I think maybe the idea is clear, right? If we have that tau is, let's see, suppose that, what do we want to show? If we have tau which is negative, right? Supposing we have tau that's negative, maybe we want to show that we're in the case where we had to have tau 0, which was positive on P0. So we're in the case that m does not halt. And I want to just mention this because I want to show where that argument doesn't work so easily. Okay, so imagine you've got tau which is negative on this. So it has to be positive on P0 for sure. That's the only negative part of this. But it doesn't have to be 0 on this. It doesn't have to come from a tracial state on A1. Okay? Because it could be like it just has to be smaller on this than it is on this. All right? And so we're in a situation where we have what's called an approximate representation. All right? We have a tracial state where the relations approximately hold. Very hard to do approximate representation theory, or at least much harder than doing ordinary, representation theory. And so the whole point of writing down these relations, there's a nice trick we can do, and I'm happy to show, you can check the paper, or it doesn't take that long to do on the board if you want to see it, okay, that we can use to say, oh, with this particular choice of relations, they happen to behave pretty nicely. We can say that if you have an approximate representation, if you have an approximate representation where the weight on these Ri's is less than the weight on these P0, this P0 part here, you had to be in this case when m halts. Sorry, you have to be in the halting case, not that does not halt case. The other part I want to say is that then the most of the work here is to show that this embedding exists. Okay, and so I think this makes a case we really need like a Higman embedding theorem for algebras like this. Okay, we have a countably presented algebra with recursively, like the relations can be specified on a computer. In group theory, that would say that it embeds in a finally presented group. But we don't have a theorem like that for algebras where we have a tracial state extension property. Okay, so that we have some work in progress where we're trying to show that this holds in general for algebras. And this is kind of the motivating example of why we want a theorem like that. Okay, so I'll stop there.
Thanks very much. Any questions?
Maybe I have a question to an early part of the talk. So how general is Halton-McCulloch theorem?
For any Archimedean algebra,
Okay.
yeah, very general.
So how come if it's the accused Fn is Archimedean, right?
Yeah.
So how come it's like?
Well, CFN, I guess, but yeah.
Why does it get so much harder, right? Because you know you have a decidability for the use the
For positivity, right?
If you remove the tracery there, right?
Yeah.
It's
Yeah, so we should think of the like tracial positivity. It's basically as hard as doing the product, and it's exactly the like in the non-local games thing where we have a correspondence between synchronous strategies and general strategies for the game, and the synchronous strategies are just on this algebra. It's exactly that style of correspondence. So the tracial states are like studying synchronous strategies, and it's really just the same as with the right constraints on the problem, it's the same as studying strategies for general bipartite scenarios.
All right. If there are no further questions, then let's thank our speaker again.